Lastly, let's look also. In this video, we will be discussing +4 corrections and the calculations that are required to complete them. Let's begin with a problem. In this problem, we are asked to complete a TL124 with a +4 correction. We are given information from our quarry or materials lab, as well as the readings on a nuclear gauge display panel shown on the right. Let's begin by filling out the known information into the TL124. Row A of the TL124 is for our wet density. This can be found on our nuclear gauge display panel and is 137.1 pounds per cubic foot. Our moisture unit mass, row B, can also be found on the display panel and is 6.9. To calculate row C, simply take A, our wet density, minus B, our moisture unit mass, or this number can be taken directly from our display panel and is 130.2 pounds per cubic foot. Row D can be calculated by taking B, our moisture unit mass, and dividing by C, our dry density, and then multiplying by 100, or by being taken directly from our nuclear gauge display panel and is 5.3%. Our maximum dry density can be found in our information from quarry or materials lab under the lab proctor information. In this case, our maximum dry density of our -4 material is 133 pounds per cubic foot, and our percent optimum moisture can also be found here and is 10.1%. To calculate our percentage of +4 material, we must first know our percentage of -4 material, which is given to us in the problem as 46%. To calculate the percent of +4 material, we simply need to take 100 minus 46, which will give us 54%. What this means is that when the material was passed through a number 4 sieve, 54% of that material remained on the sieve and 46% of the material continued through. This would mean that our percent of +4 material is 54% and can be entered into row G. In this problem, we will have 4 pieces of information that we will need to complete it. The first, P sub C, is the percent of +4 material expressed as a decimal. We've found this number to be 54%, and as a decimal would be 0.4. D sub C, which is the dry density of the +4 material, can be found by taking the specific gravity of the +4 material, which is given to us in our problem as 2.4, and multiplying it by 62.4 pounds per cubic foot, which is the density of water. When we complete this calculation, we get a value of 149.8 pounds per cubic foot. P sub F, our percent of -4 material expressed as a decimal, is just our 46% converted to a decimal, or 0.46. Lastly, our maximum dry density of our -4 material can be found under the lab proctor information and is 133 pounds per cubic foot. Now that we have all of the information that we need, we can begin plugging these numbers into our equation. In the numerator, we will first take D sub F, which is 133, and multiply it by D sub C, which is 149.8. In the denominator, we will take 0.54, which is our C, and multiply it by D sub F, which is our maximum dry density of the -4 material. We will add to that 0.46, which is the density of our +4 material, and we will multiply that number by D sub C, which is our 149.8, the density of our +4 material. We can work these problems out. The numerator becomes 19,923.4, and the two parts of the denominator become 71.8 and 68.9. When we add the two parts of the denominator together, we get 140.7. And when we do the division, we find that our maximum dry density is 141.6 pounds per cubic foot, and this can be entered into row H of our TL124. Next, we'll be looking at how to correct optimum moisture. The moisture range for this, because we are dealing with aggregate, is going to be plus or minus 2% of our corrected optimum moisture. The first piece of information is our percent of +4 material again, which is just 0.54. The next piece of information that we're going to need can be somewhat tricky at times. The reason for this is that what you are going to do is going to depend on whether or not you are dealing with soil or aggregate. With aggregate, to convert this number to a decimal, we must first add 1 to the number. So we would take our 0.2, add 1, which would give us 1.2, and then we would convert that to a decimal, which would be 0.012. If we were dealing with soil, we would not add 1 to that number before converting it to a decimal. This is only done for aggregate. The next piece of information we'll need is our percent of -4 material expressed as a decimal, which again is just our 0.46. Lastly, W sub F is our optimum moisture of our -4 material converted to a decimal. This is our 10.1%, and as a decimal, 0.101. To plug these numbers in, we can begin with P sub C, our percent of +4 material, multiplied by 0.012, our absorption of our +4 material, plus 0.46, which is our percent of -4 material, multiplied by our optimum moisture of -4 material, which is 0.101. The first half of the problem comes out to be 0.0065. Second part comes out to be 0.046. And when those are added together, they come out to 0.0525. We then multiply that number by 100 to find our optimum moisture, which in this case will come out to be 5.3% and can be entered onto line I of our TL124. Lastly, let's look also at our moisture range now that we've corrected our optimum moisture. The moisture range for this, because we are dealing with aggregate, is going to be plus or minus 2% of our corrected optimum moisture. This means that our optimum moisture range would be 3.3 to 7.3%. To calculate rho J, our percent dry density, we need to take C, our dry density of 130.2, and divide it by our corrected maximum dry density of 141.6. When we do this and then multiply by 100, the answer comes out to 91.9% and can be entered into rho J. This number will then be compared to our percent minimum density required, and as long as our rho J is greater than our rho K, we're in good shape and the test would pass.